As mentioned earlier, the Schrödinger equation is only applicable for particles moving at speeds much less than the speed of light. It's a non-relativistic, low-energy equation. Hence, there arose a need for a quantum mechanics theory that adheres to the principles of special relativity. Around that time, two individuals independently derived a relativistic version of the Schrödinger equation. Though the resultant Klein-Gordon equation solved the problem of relativistic covariance to some extent, it still had two major flaws: the inclusion of negative energy solutions and the appearance of negative probabilities. Ignoring the negative energy for a moment, the concept of negative probabilities is simply illogical. Therefore, for quite a long time, the Klein-Gordon equation was considered to lack physical relevance. However, a young man named Paul Dirac soon resolved this issue. Born in 1902, Dirac was a few years younger than Heisenberg and Pauli. He was known for being reserved, which might have had to do with his father's strict and authoritarian demeanor. However, Dirac excelled in mathematics from a young age. Initially interested in relativity during his time at Cambridge, he encountered Niels Bohr's ideas about atomic physics and was deeply impacted, thereby embarking on the irreversible path of quantum theory. After earning his doctorate in 1926, Dirac moved to Copenhagen to collaborate with Bohr. There, he used his robust mathematical skills to develop a unified theory encompassing both matrix mechanics and wave mechanics, mathematically proving their equivalence. He then solved many problems in quantum mechanics, including the aforementioned issues with the Klein-Gordon equation. In 1928, 2 years later, Dirac proposed a relativistic equation for electrons, which successfully unified special relativity and quantum mechanics for the first time. His equation also resolved the issue of negative probabilities that plagued the Klein-Gordon equation. However, it still had one bug: the problem of negative energy. This issue of negative energy later predicted the existence of a mysterious form of matter in the universe, antimatter. Dirac was initially puzzled about why electrons should have a negative energy solution that couldn't be ignored. If such a negatively charged electron moved in an external magnetic field, it would behave as if it had a positive charge. What could this particle be? At first, he suspected it might be a proton, but quickly ruled that out due to the vast mass difference between protons and electrons. If electrons could exist at negative energy levels, then theoretically, any electron could transition to such a level by emitting a photon. If all electrons in the universe did so, it would be disastrous. Dirac even calculated that, if this were to occur, our universe should have been annihilated in a fraction of a second. Hence, he theorized that in the real world, electrons could only exist at positive energy levels, and those with negative energy might be hiding in what we consider vacuum. According to Dirac, what we call vacuum is actually teeming with electrons in negative energy states. These states are filled, adhering to the Pauli exclusion principle, which is why ordinary electrons cannot transition to these levels. This hypothetical sea of negative energy electrons was termed Dirac's sea. Continuing from the concept of Dirac's sea, if a high-energy photon were to strike it and get absorbed by a negatively charged electron, propelling it to a positive energy state, this electron would emerge from the vacuum as an ordinary electron, leaving behind a hole in Dirac's sea. This hole would exhibit properties opposite to those of the surrounding negative energy electrons, essentially having positive energy and positive charge. This led to the concept of positrons. This also neatly explains the nature of electron-positron annihilation, where an electron fills the hole, transitioning from a positive to a negative energy state, while releasing photons and energy. Isn't this explanation elegant? In a 1931 paper, Paul Dirac predicted the existence of a yet-to-be-discovered particle based on the concept of holes in Dirac's sea. This particle would have the same mass as an electron but opposite charge, and upon collision, the two would annihilate each other. Sure enough, just a year later, American physicist Carl Anderson discovered the positron in cosmic rays, earning him the Nobel Prize in Physics in 1936. The positron was the first discovered form of antimatter, providing evidence for the existence of antimatter at the time. However, It's important to note that although the discovery of antimatter is related to negative energy, antimatter and negative energy, or negative matter, are not the same thing. Antimatter still has positive energy and a mass greater than zero, attracting rather than repelling in a gravitational field. In contrast, negative matter would have negative mass, repelling rather than attracting. If you release a hydrogen balloon, it floats away. But with antimatter, the problem isn't just that it will float away, it's extremely dangerous. If it encounters regular matter, they will annihilate each other immediately, converting their mass completely into energy at 100% efficiency. By comparison, the mass-to-energy conversion rate of the much-desired nuclear fusion is less than 1%, making it seem like a toy. A single gram of antimatter reacting with a gram of matter would release energy equivalent to 3 Hiroshima atomic bombs. In reality, antimatter can barely exist naturally, or is extremely rare, because it will quickly annihilate with regular matter. However, scientists can now artificially produce particles of antimatter in laboratories, including antiprotons, antineutrons, and even antihydrogen atoms. For example, in 1955, physicists Emilio Segre and Owen Chamberlain at the University of California, Berkeley, produced and discovered antiprotons using a particle accelerator, winning the Nobel Prize in Physics in 1959. In 1995, researchers at CERN produced antihydrogen atoms by having prepared antiprotons react with xenon atomic nuclei, which initially produced a pair of positron-electron. If the positron happens to be captured by the antiproton, it would form an antihydrogen atom. As one can see, the chance of forming an antihydrogen atom in this process is extremely low. Currently, producing antimatter is highly energy-consuming and expensive, making the sci-fi idea of using antimatter as an energy source impractical for now. Besides the difficulty in producing it, storing antimatter is another challenge. Any container made of ordinary matter would instantly annihilate upon contact with antimatter. So, electromagnetic fields are generally used to isolate antiparticles in a vacuum, preventing them from coming into contact with normal matter. Though antimatter is rare now, it was almost as abundant as matter in the early universe following the Big Bang. If all of it had annihilated, the universe would only consist of energy, with no matter remaining. Fortunately, due to some unknown reason at that time, the symmetry between matter and antimatter broke. Slightly more matter was left over than antimatter, allowing some matter to remain after the complete annihilation process. The universe as we know it, with all its celestial bodies and elements, is made up of this residual matter.